Hello everyone, in this video I'm going to be talking about, hang on, let me get rid of all this stuff here. In this video I'm going to be talking about Bond's enthalpy. I'm sure you could read that from the title, but the stuff was blocking it. So what Bond enthalpy is that it is the amount of energy required or released to break or make a bond. The reason why we say required or released is because when you make bonds, you release energy, and when you're breaking bonds, you require energy. So I'm going to show you a little visual here. So let's talk about breaking bonds. So when two things are bonded together, they're relatively stable for the most part. You know, if the Lewis structure is the most stable it can be, they're going to be stable. So let's take O2. Just write that this is O2. So O2 is happy to be bonded together. They have their octets all good. Actually, O2 has a double bond, but we'll just put the one bond just for reference, right? They're bonded together. That's what that one bond will represent for us right now. So they're bonded together, they're happy. When something is stable and you go to make it unstable, that isn't favored, so you're going to require a lot of energy to do. Professor Sherlock likes to use the ball rolling down the hill. So let's say that going downhill is favored because it doesn't require any energy. To get the ball to roll upwards, you're going to have to put in energy. So that's just like a way of visualizing something that's favored versus something that's not, right? Going up the hill is favored, going down the hill is not. Or vice versa. Going up the hill is not favored, going downhill is favored because it doesn't require energy. So these are already stable. We break them apart. It's going to require energy to do that because they were already stable. Making bonds is going to release energy. So I always like to say releasing energy is kind of like atoms' ways of being happy and being stable, right? So these oxygens that are floating around, they're not happy because they're going to have charges, right? They're floating around, they're not happy because they don't have their valence electrons. Their 8 valence electrons that they want. You know, oxygen only has 1, 2, 3, 4, 5, 6 electrons on its outer shell. So it doesn't have that 8 that it's happy with. So it's floating around unhappy. When you go to marry or put these two oxygens together via a bond, that's going to release energy because it's happy that happened, right? So again, breaking a bond requires energy and making a bond releases energy. Okay, so therefore we have the equation that the enthalpy of a reaction is going to be equal to the sum of the bond enthalpies of all of the reactants minus the sum of the bond enthalpies of the products. So when we have a reactant, we're going to be breaking those bonds, so it's going to be positive. And then when we have the products, we're going to be making bonds, meaning that it's going to be negative. So that's why we have that negative here. Professor Sherlock also likes to use that the heat of the reaction is equal to the breaks minus the makes, which also makes sense, right? Products were making bonds, reactants were breaking bonds. Whatever works easiest for you, I would say go with that, but just remember it's the sum. So that's why we use the plural breaks. So I just want to point out that these will be provided on our test. We don't have to put this on our note sheet. Professor Sherlock will be giving us the bond enthalpies for each that we'll need. We're not expected to memorize them and everything, so yeah. So let's go over the one that we did in class, because I think this is actually a pretty fun one to talk about, which I'll explain once we're done. All right, so first let's look at these molecules, right? So I'm going to draw out what we call peroxide, which looks like this. The reason why the hydrogens aren't in the center is because hydrogen can only have one bond to it. So I put both of the oxygens in the center. Now let's look at O2. The O2 is going to look like that, plus H2O. So you're going to have to get really strong with your Lewis structures. I'm just going through the Lewis structures quickly because I personally know what these molecules look like, but you could go through the whole process of doing the counting the valence electrons and then subtracting what you made, putting down the remaining electrons, moving things around so there's no formal charges. You would end up with these 3 if you were to go throughout that whole process. All right, so let's look. which bonds are we going to break? So we're going to break an OH bond, an OO bond, and another OH bond. So we're going to have 2 OH bonds broken plus 1 single bonded oxygen. Alright, so now let's look at what is made. So we have a double bonded oxygen. So just so that you know, a double bond doesn't mean that there's going to be 2 of the same bond. Double bond is much stronger than that of a single bond, so we just say that it's going to be 1 double bonded plus an OH and another OH. So there's 2 OHs, so we'll do 2 OHs. Alright, I just want to go back over here. This wouldn't be 1 because I just realized that it was given in half a mole, so it's going to be 1/2. Okay, so now what we have to do is we have to reference our table. So let's do OH first because we have a lot of those. Let's find the bond enthalpy of OH. It might take me a second because there's a lot going on here. Alright, OH, 460. So we're going to have 2 460 plus, I'm going to write 1, I'm going to leave a little space there, and then 1/2, I'll leave another little space there, plus 2 of that same 60. I'm also going to add in here that these are together, and we're subtracting like that, right? Because we have to do the sum of those, and then we have to subtract that from the sum of these. Alright, so now let's go and we're going to do the single bonded oxygen, which should be up here. So we have 142. And I just want to write a note here. These are all in kilojoules per mole. So our final answer will be in kilojoules per mole. Alright, so double bonded oxygen is going to be 498.8. Is that what I read? 498.7. 498.7. Alrighty, I'm going to get my handy-dandy calculator, and I'm going to multiply these out. If my calculator would turn on, that would be great. Alrighty, so we'll do 2 times 460. We're going to get 920 plus 142 minus 498.7 divided by 2, we're going to get 249.35 plus 2 times 460, 920. Let's add those together. So we have 920 plus 142. It's going to be 1,062 minus 149.35 plus 920 of 1,169. Nice. 35. Alright, so now we're going to subtract those two. It's a lot of algebra and arithmetic, which is not my favorite topic, but so it's a little bit of a process. And I'm going to say that the answer is 107.35. But let's take a look at our sig figs because we're dealing with numbers here. The highest amount of sig figs that we have is technically 2, but I'm going to assume that there's a decimal point there. I don't know if they give them in decimal points, but most of these have 3 sig figs. So I'm going to give my answer in 3 sig figs. So the answer is going to be negative 107 kilojoules per mole. And the reason why I think that this one is so fascinating, so we can see that the enthalpy here is negative. So we have a negative delta H for the reaction. That means it's going to be spontaneous. So what this is peroxide. It's what we call hydrogen peroxide. Hydrogen peroxide. I'm sure you guys probably have this in your bathroom cabinet. If not, maybe that's where we're different, but most people have this in their household, or they've heard of hydrogen peroxide. So I know in my family we use hydrogen peroxide like to clean wounds sometimes, or like for me, like I will get like one really giant pimple like randomly throughout the year. Like I usually don't get much acne, but my mom always tells me to put hydrogen peroxide on it. And that's because it's very volatile, which means that it just dissolves really quickly, or evaporates really quickly, so it dries out your skin a lot. But hydrogen peroxide does go bad, and the reason why it goes bad is because spontaneously, so the most favorite thing is for oxygen to get released and to be left with just water. So after a few years of hydrogen peroxide, if you leave it out in the open for a long time, it's just going to turn into water. All of the oxygen is likely going to just evaporate, and it'll become water. If you take Gen Chem 2, you're going to learn that there's things called equilibrium. So it's possible that the oxygen is going to rebond with the hydrogen, but that's only if there's enough energy. So that's where those things. But I think that this is like a very fascinating one to do because of that. All right, let's go over this one. So we have C2H4 plus HCl, hydrochloric acid. That's going to yield C2H5 and Cl. All right, so let's draw these out. I'm going to make these H. And the nice thing about honestly getting like the chemical formula and when there's only hydrogens is the fact that these can't be double bonded. So both these carbons aren't happy. So how we can fix that is just adding a bond. That's like my fast way of doing that without having to do any of the valence electrons, but whatever you guys feel comfortable with. Again, do whatever you need to get these Lewis structures. Now let's do CC. 1, 2, 3, 4, 5, 6. All of the carbons have everything. This will probably have electrons on the outside, because that's what chlorine does. Alright, so let's talk about which bonds are made and which bonds are broken. So it looks like we're going to have 1, 2, 3, 4. So we're going to have 4 carbon-hydrogen bonds plus 1 carbon double bond. Also in the reactants, we're going to have 1 hydrogen chlorine bond. So 1 hydrogen chlorine bond. Alright, so we're going to add all those together and subtract it from these bonds here. So we're going to have 1, 2, 3, 4, 5. We're going to have 5 carbon-hydrogen bonds, and then we're going to have 1 plus 1 carbon single bond plus 1 carbon chlorine. 1 carbon chlorine. So there's a lot going on here. So I'm going to check myself by counting up the bonds. So I have 4 plus 1, 2, so 6, 7. 1, 2, 3, 4, 5, 6, 7. Awesome. All right, and then here I have 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, cool. So I don't think I forgot any. That's always nice to establish. All right, so let's do this one. All right, so we're looking at the carbon-hydrogen. The hardest part when you're given a chart is just finding where they're going to be. So carbon-hydrogen is 414. So we're going to have 414 plus 1 carbon double bond, 620, plus 1 hydrogen chlorine, 431.9, We're going to subtract that from, we already know what the carbon-hydrogen one is, so I'm not going to look that one up again. 414 plus 1 carbon-carbon we haven't gotten yet. Carbon-carbon single bond is 140, Jesus Christ. 347, that's how you say that number. 347. Alright, and then finally we're going to have carbon-chlorine, carbon-chlorine. I was like, carbon or hydrogen? Carbon-chlorine. Carbon-chlorine, where are you? Alright, 339. Alright, so again, I'm just going to check myself again. So we had carbon, hydrogen. Let me just make sure all these are right. Carbon, hydrogen, 414. Carbon double bond. The reason why I'm checking myself because there was a lot in this one. Carbon double bond, 620. Carbon or hydrogen, chlorine, 431. Same thing, 437. And that was carbon single bond. Okay. 339. Okay, cool. So all those were right. All right, let's go about adding these together now. So 4 times 414. It's a big number. We have 1,656 plus 620 plus 431.9. We're going to subtract that from our 5 times 414, an even bigger number, 2,070 plus 347 plus 339. Alrighty, 1656 plus 162 plus 141.9. Okay, I added in right. Alright, 2707.9. I'm gonna double check myself there because I said something but wrote something else down. 431.9. Alright, got the same thing. Minus 2070 plus 347 plus 339. Oh, this one's interesting. Alright, so we're going to do 2707.9 minus 2756. Wow, that one's actually pretty cool. So our found delta H is going to be equal to 48.1 kilojoules per mole. So after we had all of those big numbers and all of these bonds, oh, it's going to be negative. Negative 48.1. After all that craziness that just went on, we just got this little tiny number. So it's pretty interesting how it releases a little bit of energy considering how much is made and everything like that. So that's all that I have for this video, so I hope this helps. Again, pretty simple concept. Really the hardest part is remembering how to count the bonds, know which bonds there are, where to find it in the chart. But yeah, so I hope you guys enjoyed, and again, if you guys have any questions, please reach out and let me know. Thank you.